Oh.
Tomorrow. Thursday.
Just the only. Yeah, that's great. The only thing is that I just organized a meeting with yes, yes, and convert it. Yes. Yeah, that would be great. Yeah, I'd love to. Is it not on? Light on? Good. And what about the presentations? We have, that's okay for tomorrow? So we're like, so we'll have this number of presentations? I'm just to plan.
Almost for the discipline, I hope that it was a bit fun.
Oh, okay. And so everybody in this room will present.
Yes.
Okay. So like, yeah, but I'm just saying, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? No. 10. 9.
Mas pode também. Então, no curso, mas não fica à vontade. Eu acho que pode fazer mais português. Eu acho que não, mas o que eu disse assim, vocês não precisam apresentar o que vocês fazem, né? Então, uma ideia que seja, que converse com o que a gente está aqui hoje, né? Você pode até usar isso depois como projeto paralelo, ou não também, assim, só para a gente exercitar esses conhecimentos antigos, né? Então, acho que é bom conectar a área futura de pesquisa de vocês. Então, fiquem à vontade. Então, acho que vai dar você seja parte da. Tem mais gente, mas eu sei que tem a primeira da Isabela, a viagem chegou hoje. Ela provavelmente vem amanhã. E deve ter mais gente, porque eu lembro que é 8 vai assistir. Não, mas eu acho que não vou falar 8. Rodrigo, mas a gente tem que Rodrigo, vocês 4 eu não sei. Ele fica da disciplina. Então, 1, 2, você também, né? Rafael? Disciplina. 1, 2, 3, 4, 5, 6. Ah, não, tá na disciplina. Nós vai apresentar. Ótimo. Então, já temos 7 presentations. And Rodrigo will send for us a 5-minute teacher.
Okay, great.
Isabela, 9. Eu mandei e-mail para todo mundo, deixar ela tá no e-mail. Talvez ela não tenha. Qualquer coisa pode falar para ela, que até as 2 horas da manhã pode mandar um vídeo. O caso, né? Ela. A gente ter a.
Yeah, that's great.
It's something like 3 like this.
Yeah, I mean, it just as whatever it takes to sort of transmit some question or something that you want to discuss about your project. Like, I always like to make it to be not just about the theory, but like, to try to help you in your research. And again, I understand that it's not always possible, but it's like, that's the goal. But if you can't do that, then it can be just a theoretical problem that you're interested in talking about. And it's just to stimulate discussion on the topics that we've talked about, right? That's like, to me, the principal goal. I think that there's other goals for grading. That's not my goal. But I think that I don't think that there's any wrong answers or wrong way to present, as long as it's like, an honest material about what you're interested in trying to improve using some of these concepts, right? Because I think at the end of the day, we just want to take one step in the right direction. And this is one way that you can think about it. Good. Okay, so let's start again. Is there any other questions or clarifications that people would like to talk about previous material, something that you thought about? Yeah. Good. So so what I'm going to talk about today is something that maybe we first learned about in high school. Oh. What is this student doing? Oh, wow. Okay. All right. That's awesome. I got to get a picture of this. Can you take a picture? Okay, so come. Oh, there we go. Oh, oh, oh. No. No, that's enough. No, come. It's like, I don't want to learn this material. I learned it already. Thank you. So what we're going to talk about today is, something that we probably learned in high school, definitely in general chemistry at the beginning of your undergraduate degree. So it's like really all review, but I just want to talk about it in terms of the concepts of green chemistry, because it's the way that we count molecules and atoms. And it's just looking at it from a perspective is like, it's not only to calculate yields of reactions. We can use the exact, the terminology and the language of chemistry that we have, which is the periodic table, the molecular weights, moles, atoms, balanced equations, and those balanced equations have a huge impact on green chemistry. It's just like we just have to think about it, sort of twist the way that we think about things. So it's going to seem, I think, rather simple, a lot of the things that we're talking about, but just in a slightly different perspective, right? So we know about stoichiometry, and calculations that we need to balance and predict reactions. So balancing the left side of a reaction and the right side of a reaction. So when we balance a reaction, what we're doing is balancing the atoms. Right, on the left side, we have a certain number of atoms, and if it's a chemical reaction, then all of those atoms have to be accounted for on the right side of the reaction. And what the byproducts are of that chemical reaction, that's the balancing act of the atoms. And then we have to think about how many atoms are being incorporated into the final product and how many of those atoms are going off to form a byproduct. We also are talking about general reaction classes. So once we get the stoichiometry, we want to think about sort of how reactions occur and which of those might be more green and less green based on this evaluation. So not just thinking about, undergraduate organic chemistry where we just basically teach all of the reactions and we don't put it into perspective is like how much byproduct is this reaction does this reaction have versus this other reaction. We just say a primary alcohol is oxidized to an aldehyde, right? But what we really need to think about is the primary alcohol is oxidized to the aldehyde and it creates this amount of byproducts. And then you can start to think about why we do research in synthetic organic chemistry. That's my expertise. That's why I talk mostly about that, but this can apply to many other areas. But that's why we need multiple ways to do an oxidation of a primary alcohol to an aldehyde, because there is this waste component and atom economy component. So there's always ways that we can improve things based on green chemistry principles. We talked a little bit about greener reagents, solvents, and reactors. I'm just going to give more specifics on this today. And then we also talked about biomimicry. So for example, the butterfly, in terms of its ability to produce color without dyes. And I'll show some more examples similar to that. And endangered elements. So if we look at the periodic table, not all of the elements are equally resourced on Earth, right? So some of them are more rare and some of them are non-renewable elements. So we need to be aware of those when we're doing green chemistry, which those elements are, we can reasonably expect to be here over an extended period of time, which ones are depleting resources, just like petroleum is a depleting resource. And so essentially the same math that we use to convert formulas to moles and balance those equations, and then that leads to product and waste. This is really also going to be able to highlight where processes are more or less efficient. So again, just the simple math is like, the periodic table. We, as organic chemists, we mostly are dealing with so again, for some molecular examples, so for example, we are telling that to get some rate, multiply two chlorine atoms, we have water, two hydrogen atoms, and one oxygen atom. Rate, sucrose, combination of carbon, hydrogen, oxygens, multiplied by each of the molecular weights on here to get the overall so basically, the molecular weight can be used for any types of organic molecules. So it's not just, any type of molecule. It doesn't just have to be organic molecules. So this is good for ions, salts, molecules, and different compounds. So again, just to give some more examples. So aluminum sulfates, Al2SO4 So in this case, we would multiply, there's two aluminums and there's two sulfates. So we can calculate the molecular weight of sulfate and then multiply it by 3, or we can multiply sulfur by 3 and oxygen by the O4 by 3. So that's where we get S times 3, O times 4 times 3, and we get the overall masses of the components of aluminum sulfate, and then we get the overall formula weight. So again, rather simple concepts that we've seen a long time ago. Where it gets more interesting in terms of how we count is Avogadro's number. And so this is just a way that chemists can convert things that are unreasonably large or unreasonably small in terms of the size of these things, and we can convert it to something which is more manageable. And so that's essentially why, it's similar to saying, a dozen eggs is a shortcut for saying 12 eggs. A ream of paper is essentially 500 sheets of paper. I'm not sure if there's a term like that in Portuguese, but it's 500 sheets of paper. It's a ream. And then, the moles of atoms or molecules is 6.022 times 10 to the 23. So it's just a crazy number, right? Times 10 to the 23. It's a number that sort of we can't easily wrap our heads around. And so that's why we use that as a measuring stick. So it's essentially like so that we know that that number represents a huge number, but we don't talk about that specific huge number all the time. And so why chemists use it is because there's 1 mole of carbon atoms, and that 1 mole weighs 12.01 grams, right? And that becomes something which is much more practical from a green chemistry perspective, right? Because we're not weighing moles. Right? We're weighing grams of material that contains a certain amount of moles of that material. And so ultimately we have to convert back to this grams, and that's why the mole is a useful tool to convert back to the grams, which is the thing that we weigh of the particular molecule that we calculated the molecular weight for before. So the mass connects formulas to bench scale masses. So we're connecting this very theoretical thing, which is the molecular formula, to something which is very tangible and measurable in a lab, which is the mass of that particular material, object, etc. And so again, just to keep us on the same page, that we can think about molecular formula representing one molecule of H2O, or it can represent 1 mole of H2O. So those are just different ways that we think about molecules. So each of them are applicable, but in both cases, the ratio of the subscripts is the same. So if it's 1 molecule of H2O is water, we know that a molecule of H2O is comprised of 2 hydrogen atoms plus 1 oxygen atom. But that's the same for moles of H2O. So it means that if we have 1 mole of H2O, it's comprised of 2 moles of hydrogen plus 1 mole of oxygen. Again, it seems rather obvious and trivial, but this is going to have impact in terms of balanced equations, and that's going to have an impact on the waste that gets created when we do these balanced equations. So again, simple calculations. But if we want to convert 100 grams of water to the amount of moles of water that is represented by that 100 grams, we multiply it by we divide it by the molecular weight, which is 18.02 grams per mole. So when we divide, we multiply by the inversion. And so it's 1 mole per 18.02 grams of water, and we get the number of moles. We can do the same thing for sucrose, and we can then convert that pounds, a very American calculation, a non-metric amount, but we can convert that to the amount of grams of sucrose that there is in 1 molecule of sugar. So again, rather interesting, right? Because we're now down to single molecules, right? A single molecule of sugar is 5.68 times 10 to the minus 22 in grams, right? So it's interesting to start to think about these things, is that if you can isolate a single molecule, that's the weight of that single molecule. So this comes to I think the much more important thing that we're talking about is balanced equations. And so if we look at these two, and again, I'm not going to go into too much detail about balancing equations. Hopefully we can sort of review what we already know and understand how to balance equations. What I want to use this more is to highlight the effects that balanced equations have on producing byproducts and therefore producing waste in chemical processes. And so if we take a look at this reaction is balanced when there's 1 molecule or 1 mole of both of these reagents. They react with one another, and it forms 1 molecule of water and 1 molecule of CO2. So what this means is that if you count all of the hydrogens on the left side, there's 2 hydrogens. If you count all of the hydrogens on the right side, there has to be 2 hydrogens, right? That's the balanced equation. There's 1 carbon atom on the left side, there's 1 carbon atom on the right side. There's 3 oxygens on the left side, so there has to be 3 oxygens on the right side. So that's a balanced equation, but if we start to think about it in terms of reactivity and waste, we are not necessarily going to be doing this reaction to produce both water and CO2, right? So we might, on an industrial scale, and this is a completely make-believe argument, but we might say to ourselves, we want to produce water from this chemical process. And so what we're saying is that the input into this chemical reaction is going to be these 2 components. So how much do they cost? Where do we get them from? Is it economical? Is it environmentally sustainable to get those 2 starting materials? That's the first thing that we have to think about. And then at the end of the reaction, we have to say that we have to dispose of CO2 because it's a byproduct. And that's why balanced equations is so important, because what you want is you want to have the most of these atoms incorporated into the target product that you actually want. And so that's why we show an example on the left-hand side where we show nitrogen reacting with 3 molecules of hydrogen. And this balanced equation, so on the left side we have 2 nitrogens. If we're producing 2 ammonia molecules, there's 2 nitrogens, and so there's 2 nitrogens on the left side, so it's balanced in terms of nitrogens. There's 6 hydrogens on the left, and there's 6 hydrogens on the right, so it's a balanced reaction. But now if we say to ourselves, well, we want to produce ammonia from this chemical reaction, we have 0 waste. There's nothing that's produced except for the ammonia. And so in terms of environmental impact, that's a huge difference than producing CO2, which this molecular weight of CO2 is more than the molecular weight of H2O. So for every time you do that reaction, the mass of product that you form is less than the mass of the byproduct. So it's a very inefficient process. And so that's why stoichiometry, balanced equations, and understanding them becomes so critical in green chemistry, and why it's important to go over these concepts in this degree. So here's just another example, and just showing you, this is just highlighting essentially the fact that we can get quite complicated balanced equations. So it's not always just 1s and 2s. So there's 4 ammonias plus 5 oxygens that make 4 NOs plus 6 H2Os. So again, what the importance is not to balance the equation, but it's just to say that if you're trying to make NO via this process or H2O versus in this process, it's going to be very different sort of calculation in terms of the waste that gets produced, because the other component is always going to be waste. Now, having said that, and this is where the petroleum industry is like, does an outstanding job, is that the petroleum industry will do a process such as this, and maybe they're making NO, but then they'll take that water and do something with that water, right? And then that way, then what's the byproduct is not wasteful. It's actually being incorporated into another process, and the waste of that will be incorporated into another process, et cetera, et cetera. And that's why the E factor of the petroleum industry is relatively small, because even if they have equations that are, even if they have reactions which have byproducts, they valorize or try to do something with that rather than just treat it purely as waste material. So again, using coefficients to turn formulas into quantitative instructions. So again, in this case, when we're talking about carbon plus 2 hydrogens to form CH4. And I think that the other thing to think about in terms of research, basic research, is that when you are developing chemistry, you are developing new processes, you should think about, this in a very theoretical way, because, carbon plus 2H2 might not be, in theory, the most efficient way or a known way to make methane gas. But it's something where it's like, if you think about it in terms of the most atom economical way to put together your target molecule, you might start to think about new research areas that say, why can't we do this in a much more direct way than, for example, doing something like that, where you have a balanced equation with a lot of coefficients, right? So it's like saying, what are the minimum number of atoms that are required to make the target molecule? And is there a simpler way we can do it than to do it from something more complex? Because the more complex, the more atoms that are involved, the more likely there are to be byproducts of those reactions. So again, this is more complex, where there's a lot more subscripts for the atoms. The balanced equations is more complex. So it's just giving you sort of another example of saying that if you are trying to do this process, the calcium, if you're, for example, if the calcium is the most expensive thing in this process, well, the 3 calcium atoms are incorporated into this calcium product. So that's effective because, maybe the cost or maybe the environmental impact of calcium. You don't want that into the waste. But there might be other processes where three of those calciums are incorporated, maybe only two of those calcium atoms are incorporated here, and one of them is generated as calcium byproduct. Well, if calcium is really environmentally unfriendly or it's rare, that's not a process that would be particularly efficient. This is for again, for those who are doing chemical reactions, relatively straightforward, right? You go into a lab, you measure the grams of some material, you convert that into the moles, because that's what the molar ratio is what you're looking at. You take the molar ratio and convert it to the moles of target, and then you convert back to grams of target based on the molecular weight of that target, right? And that's how you convert directly from something you measure as the measurable starting materials. Then you convert it to the molar ratio, convert it based on the stoichiometry of the reaction, and then convert it to a mass of something that you can weigh at the end, which is the mass of your product and the mass of the byproducts. So how much H2O forms? So this is just an example, is that if we take a look at how much H2O forms when we use 5.44 grams of oxygen in this reaction. So the first thing you should always do is to make sure that the equation is balanced. And so counting the number of atoms on the left and the right side. If it's balanced, then you could go on to converting that to the number of how much water is produced. So we know that there's 5.44 grams of oxygen. We multiply it by the inverse of the molecular weight of oxygen, which is 32 grams per mole. There's 6 molecules or moles of water per 5 molecules of oxygen. You multiply that by the molecular weight of water, which is 18 grams per mole. And when you do this and you cross out moles of water, moles of water, moles of oxygen, the 32 grams of oxygen, grams of oxygen and grams of oxygen. So the only thing that you're left with is grams of H2O. And so this is the 3.67 grams of oxygen. So, what's interesting too is that if we're thinking about this in terms of green chemistry, is that we have to, even though this is a balanced equation, but we have to say to ourselves, the mass of oxygen that we have to use is 5.44 grams, but we're only getting 3.67 grams of water out of this process, right? So again, that's where it's like this disconnect, because we are balanced. So there is 6 moles of water versus 5 moles of oxygen and the balanced equation. So you think that in a molar sense, there's more moles of H2O that are being formed than oxygen, but there's less mass. And at the end of the day, mass is what we extract from the earth, right? We don't extract moles from the earth. And so that's an important equation, an important concept to consider, is that we have to, even though the balanced equation has to come from a molar ratio, but the practical implications comes from the grams of material that is either reacted or creating the waste. Here's just another example. Again, nitrogen dioxide reacts with water to form nitric acid and nitrogen monoxide. So here's a balanced equation. There's 3 NO2s that form 2 HNO3s. So if we want to produce 1 kilogram of HNO3, we essentially have to produce, we have to use 1,095 grams of NO2. So again, this is just the way that we convert from mass to moles and then back to mass in terms of either the front or the back reaction. And so we can do this in both ways. We can either say how much do we need to make this, or how much will this, if we use a certain amount of this, how much of this we will make, right? So we can look at it back and forth. So this is just another example of essentially how much grams of oxygen react with acetylene. And this is just to show you, for example, is that the inputs, so what the amount of stuff that we use is going to vary greatly based on both the molecular weight and the molar ratios of the starting materials. So here, if acetylene is being used in 52 grams, we need to use 160 grams to make the corresponding amount of CO2. So it's just to say that, again, the weight of the starting materials is not based necessarily on the smaller molar ratio, right? It's really dependent on the amount that we use, the molecular weights of those components. And so 52 grams needs 160 grams of oxygen. So whichever of these is more environmentally unfriendly, it's like it could be more problematic or less problematic, right? Because you need to analyze those two components simultaneously. Okay, so all of that said is that then it comes down to we can then categorize reactions, chemical reactions, into general reaction classes. And so it's just saying that the formulas can help predict the products. And so here we have barium chloride and H2SO4. And essentially what's happening here, this is more of an inorganic reaction, that the two chlorine atoms are being replaced by the sulfate that's shown here. And so we have barium sulfate that's being formed from barium chloride, and the byproduct of this reaction is two molecules of HCl. And so if you think about the barium is essentially one atom of barium here is going to one atom of barium there. So if this is likely to be the valuable product in this process, you can see that we haven't lost any barium atoms. We've only lost chloride atoms as an HCl byproduct. So this is essentially a very simple representation of many of the organic reactions that we see in our undergraduate degrees for sure. And so it's a generic way of looking at things. So we can have combination reactions where two starting materials essentially combine with one another to make a product that's shown here. We can have a decomposition, or essentially the reverse reaction of the combination, where XY is split into two individual components. We can have a single replacement. This is something like the SN2 reaction. So where X comes in and displaces Y. So we make a new XZ bond and we break the ZY bond and we release Y as a byproduct. We can have a double displacement. So each of the components are displacing one another. So we get AY and BX as products here. And then we can have combustion processes, which are oxidations of fuel sources. So these are essentially ways in which we can have carbon input and then oxygen, and that makes carbon dioxide plus H2O. So if we think about these reaction classes in terms of green chemistry and atom economy, what do we think about the atom economy of a combination reaction? Is that economical from an atom economy perspective? It's atom economical, right? Because X and Y are coming together and both X and Y are in the final product. What about the decomposition? Is that atom economical? I think the real answer is it depends, right? Is X and Y important products? If they're both important products, then it's atom economical. If only X or only Y are valuable, then it's not atom economical. However, having said that, it depends on what X and Y are, right? Because X and Y, I've drawn them as letters, but X could be a huge molecule, part of the molecule, and Y could be a part of the molecule, right? And if that's the case, then maybe X being a valuable product might be okay because you're only having a little bit of Y as a byproduct. The molecular weight's a little low. But what if it's the reverse and Y is the valuable thing? and you have this giant X molecule that's the byproduct, right? So I would say that the decomposition process, it's questionable whether it's atom economical or not, highly dependent on situation. What about a single displacement? Single displacement, same, kind of dependent, right? It depends on what it's going to be, but again, certainly neither of these is going to be as good as combination, right? Combination is certainly better than both of these so far, but single displacement, same sort of problem. Double replacement, same sort of potential problem here. The combustion is, if water is the byproduct, essentially you're using a lot of your oxygen to get into CO2. So if CO2 is your product, it's a fairly efficient process, combustion, right? It depends on the energy inputs, but from an atom economy perspective, it's relatively atom economical. So what are some of these specific reactions that are that have the combinations? And so one of them is hydrogenation reactions. So that's where we add hydrogen across a carbon-carbon double bond. So we add a hydrogen on this end, a hydrogen on that end. If we source the hydrogen source from H2, then essentially all of the atoms are incorporated into the final product. So this is one thing which I think is, from an academic perspective versus a practical industrial thought process, is the fact that simple reactions tend to be much more atom economical, right? So when you get the more exotic you have your reagents, the more exotic the catalysts are, the less atom economical it becomes. And that doesn't mean that it's not practical, but it just means that sometimes very simple reactions that we learned that were discovered 100 years ago are still very useful to this day. Bromide, dibromide addition. So this is the same type of reaction where we're adding 2 bromine atoms across a carbon-carbon double bond. The alcohol addition across a couple carbon-carbon double bonds. So here we add a hydrogen on one end and we add an OH group on the other end. So again, all very atom economical. But again, just like I said before, yield is not the only way that we measure efficiency of a chemical reaction. Atom economy is not the only way too, right? We have to think about other factors like E factor, and then we have to think about where these chemicals are sourced from. So where do we get this bromine? Is that a sustainable process? Where do we get the hydrogen gas? Is that a sustainable process? So again, just to make sure that we put into our minds is that we can't look at one parameter when we're talking about green chemistry. We have to take all of these parameters into consideration. So some reactions that are influenced by byproducts and waste. So both elimination reactions, so breaking down something like compound A into B and C, we're going to be creating a lot of waste. And then substitution reactions, essentially AB and CD, where we substitute each of them with one another, again, can create a large amount of waste if the byproduct is not the valuable product of that chemical reaction. So this is like, one reaction that we learned at the undergraduate level is the Friedel-Crafts reaction. This is a highly valuable reaction industrially to functionalize benzene rings. So to make more derivatives of benzene, but the reaction is not atom economical. And so that's why, again, this is part of the thing in terms of like if you want a research project that could have impact, is that you should, if you evaluate things based on green chemistry, I think it will lead you to ask questions of, can this be done in a more atom economical way? Can this be done with a lower E factor? Can this be, and if you start to ask those questions, you can start to contribute to solving some of these open questions. So lab versus nature. So this is, again, this question of natural versus synthetic, which is better. And the real question is not which one is better. It's the question is which design principles can be used, can chemistry borrow from? So essentially, how can we use nature to inspire chemists to do things in a more efficient manner, right? So it's not that one is better. So, photosynthesis is, an amazing process that harnesses energy from the sun that plants use all the time. And so then the question is, can we understand that in a sufficient manner that we can try to replicate that with a synthetic process that mimics the biological process of harnessing that energy? And so there's lots of different examples where scientists have taken this inspiration from natural sources to try to create more efficient and green processes. And so, this is essentially, a lot of the differences between what nature often does and what laboratory synthesis often use. So typically nature is not doing things under pressure and is doing things at relatively ambient temperatures. So, between 20 and 40 degrees Celsius is a typical way that a biochemical process will occur. Water is the typical solvent. But one thing that's interesting, and a colleague of mine is studying, is that even though water is a solvent for many biochemical processes, what seems to be more important, and this is one of the things that's challenging in biochemistry, is that we take these enzymes and biomolecules and we then create buffered systems to try to study them outside of a living system, right? And we have to do that because it's not easy to study them inside a living system. But what happens is that we've created an environment which is so unlike the living system that it might not be a good representation. And what she has found is that she thinks that proteins exist more like slurries. So rather than exist as sort of a discrete solubilized molecules in water, they behave more like if you put a little bit of water and sugar. Right? If you put a little bit of water and sugar, you can stir that sugar around, but the sugar doesn't completely dissolve. And her feeling is that proteins behave more like that than they do as completely dissolved sugar in water. And that means that that is much more like solid state chemistry than it is like solution chemistry. But most of the biochemistry that we do today is much more like studying enzymes in solution, which might not be a true representation of what enzymes behave like in a real living system. So enzymes and cascade reactions. That's one thing that nature does very well, is does a series of chemical reactions on one starting material to get a complex target molecule, whereas in the lab we tend to do one step at a time. So we make one derivative, we purify it, we analyze it, we make another derivative and another derivative. That all costs solvent, time, and energy. Nature has usually high selectivity. Now the problem, not the problem, but the balancing act is that nature is designed oftentimes to be very selective to make a single final product, right? That enzyme has evolved over thousands, millions of years. So it's not surprising that it can make a single molecule. But what it's not good at is then if I want to make that molecule with an extra methyl group, because that enzyme is so critically evolved to make that molecule without the methyl group. And so the question becomes, can you modify the enzyme so that it can make a broader range of targets effectively, right? And that's something which enzyme evolution scientists are working on, and I think it's a really interesting area. Nature doesn't tend to purify after each step. It essentially just makes the product. There's minimal waste in many of the pathways, and in many of these biochemical pathways, not only is there minimal waste, but usually when there is waste, that waste is siphoned off to another biochemical process. Whereas in the organic labs, we tend to have precious metal catalysts that can be, that needs to be disposed of or tried to be recycled. Okay, so if we want to improve reaction design, it's not a single thing that you're going to be able to do, a single design feature that will improve it, but it's always going to be a combination of everything, and not all of these will apply to all processes, right? So that's the thing, is that we can't let, I think the saying is, we can't let perfection get in the way of progress, right? Because if we wait for the perfect solution, then we won't actually progress. So it's like we're not looking for perfection, we're looking for progress, but these are the key ideal features. So we want high yield and high selectivity. So 100% yield and no byproducts, right? That's why selectivity is so important. We want low or no waste byproducts. We want earth-abundant feedstocks, so things that are both abundant and renewable. This is both in the starting material and any catalysts that we use. We don't want to use any high energy sources, so not to do things at high temperatures or low temperatures. We want to remove solvent completely or make a much safer and recoverable solvent. We want minimal separations, so minimize the use of chromatography and minimize any purifications, solvents that we need. And so essentially, again, what we're looking at is life cycle, so the impact overall of the process, not just on single factors like yield or atom economy or E factor. The feedstocks, like this is starting to change the upstream burden. So essentially, a lot of the chemicals that we get from for our research in the lab currently, if you traced back, and I think it's an interesting exercise, is to say to yourself, I bought this from whatever company, and then say to yourself, but where did this material come from originally? Like industrially, if I have to go back 2 or 3 steps, where is it originating from on this earth? It's not originating from that company, right? That company bought it from another company, which derivatized it, and that bought it another company. And if you go back far enough, most of those chemicals that you are looking at today came from a petroleum-based starting material, right? And so that is going to change over time. And the starting materials we need to start to use are things like agricultural waste, municipal waste, food waste, CO2, carbon capture is another interesting carbon source, and then other other things like algae, switchgrass, hemp, so stalks, and non-competitive biomass sources. So this is a key concept, right? Because biomass sources, it kind of is a catch-all for saying that that's a good thing that we're using biomass sources, but there's the trade-off of biomass. If we're taking that away from food supply, that's not necessarily a good thing, right? So we have to say to ourselves, how are we going to use the land that we have? And we have to feed people. That's very important. But then we have to produce alternative feedstocks for the chemical industry. And how do we balance those two? This is a little bit like I alluded to last class in terms of solvents. So going into a little bit more detail is to say that this solvent choice, and again, I think that somebody was asking about optimization of the reactions and should you think green, right? And I think that it's one of those things where some of these factors that you know about them now, it's like, I think that it's relatively simple when you're starting a project to say to yourself, okay, I know there's lists that tell me what are the preferred solvent choices, what are the usable ones, and which ones are the undesirable ones. Like that's a good starting point, because then at least you can say to yourself, you know what, I'm going to go in the literature and I'm going to find, because the problem we have right now is that a lot of our literature, which is pre-2010 probably, didn't take into consideration green chemistry concepts at all. So you go there and they were using whatever solvent that they wanted that would make their reaction work. And that's fine. Not fine, but that's the way it was. Like we can't go back and change what's happened. But what we can do is now we go in the literature and we have to do something today, develop a new chemistry. And what we can say to ourselves, okay, I can go back to the old literature and see what they did, but there's going to be many ways to do what you want to do based on the old literature. So now I'm going to prioritize it based on which one of those examples we're using these solvents. And that's the ones I'm going to do. And any examples that use these solvents, I'm not going to do them unless you go in the literature and you say to yourself, okay, everything that's in the literature suggests that I have to use one of these solvents, right? But then that becomes sort of an open new research question, is that maybe they did that 50 years ago because that was the solvent that they had in the lab and they didn't think about green chemistry and they never tried anything else. So that's maybe a potential research project that you're like, oh, nobody's ever done this in a solvent that isn't this, so let me try these new solvents, and maybe that's a small contribution to green chemistry that I can demonstrate this reaction that's never been shown to work in green solvents can be done in green solvents. Maybe you have to modify those conditions, maybe you have to improve those conditions, but maybe you can, start to think about it that way. So, these are examples of sort of what industry would say is more preferred solvents. These are relatively useful solvents that they would use in exceptional cases, but these are the ones that they typically want to avoid in most cases. And again, I would say that this list is constantly evolving, right? So this is not, I wouldn't take this slide as being the decision point. I'd go into the recent literature and you can find many papers that will show this sort of analysis, and each analysis might be slightly different, but in general, this is the way that solvents are prioritized industrially. Microwave reactors, so this is another interesting way to reduce energy costs. So rather than heating your reaction by using an oil bath or using a heating mantle, you can use a microwave reactor, and that microwave reactor will create an energy source that's can be less expensive than traditional heating. So again, you have to be careful because a lot of people claim that microwave is just a more green way of heating, but you have to consider the life cycle of the microwave reactor, right? That microwave reactor didn't just come from nowhere. It had to be manufactured. What's the cost of the manufacture? What's the life cycle of that, and can that microwave then be reused? And on top of that, microwave reactors have a limitation of scale, so sometimes you can do things very well on a lab scale, but industrially to do microwave reactions, it's not as trivial as doing it on a lab scale. So again, just to think, to always put in that question, is this really green? It certainly can be considered green, but you have to think about it in the bigger picture. Microfluidics, so this is a very interesting way, is that you can make these sort of very small channels, and then you could load in these channels reactants, and then they essentially would flow via it can be a variety of different processes. So this could be done by charge transfer. This could be done by vacuum. There's a lot of different ways in which you can put the drops of the starting material that you need, and then it flows in a certain direction. They react, and then it comes out at some other point. So this is interesting, very interesting if we think back to the accidents that we saw previously, where you had these giant containers of methyl isocyanate, some very toxic material. So now if you think about microfluidics, you can keep much smaller amounts of these material because essentially you're dropping the material, it's going into the flow reactor, and it's reacting as quickly as you're dropping it. So the amount of material that you need would be a lot less. You wouldn't need to store, because you could just bring it in, microfluidic it, react it, and then you don't have any excess material stored on site. So this is an interesting way. There's other advantages where there's faster mixing, lower energy demand, the inventory is lower, there's usually less higher purity and workup, and but of course, like everything, is that nothing is perfect, and that means that if you have a small tiny particle in this microfluidic system, it could clog the whole system, right? So this has to be a system where everything is completely solubilized, which means that by definition, you typically need to use solvent for this reaction. Because if you do it without solvent, then it's too viscous and or too problematic where solids could form. So again, nothing's perfect, but all nice tools to have to push things towards improved green chemistry. Flow chemistry is essentially similar to microfluidics, and so essentially what you're doing is you're mixing your starting materials and you're putting them through tubing, and that tubing then can be, you can do a lot of different things in terms of flow chemistry, is that you could put the tubes and pass the mixture over top of solid catalysts or solid acids or solid bases. You can put it in line with purification. So essentially you mix your two, and this is being pumped through with a loop. And so the reaction is occurring in the flow system, maybe over a catalytic system. Then afterwards, you can maybe immobilize your product on a solid support and then remove it from that solid support. So you can do the whole process in a continuous flow system. And this really would minimize solvents. And it's really one of those things where it produces the product on demand. And that's industrially, this is increasingly becoming important, because now instead of doing a reaction, for example, if you do a typical organic reaction, that might be 12 hours. And so if you do that in the traditional way, where you're converting something which you're doing in a round bottom flask with a stir bar, so you take that and you scale it up into 100 liter vat. Well, you have to do that put everything into that 100 liter container, mix overnight, then take everything out of that container, keep feeding the system. And if you just keep feeding the system, you could maybe make 1 kilogram per hour or 1 kilogram per day, but you don't have to actually stop the system, right? If you want to make 2 kilograms, you just keep injecting starting materials and it flows through the reactor. And so instead of doing a bulk reaction, that can save a lot of time and energy. So that's industrially, this is becoming much, much more useful and much more important. So just some of the advantages. So faster reaction times, better mixing and heat transfer. Again, we have smaller inventory of hazardous material. It can be higher reproducibility, and in some cases less workup. The constraints, as in everything, there's nothing that's perfect, so you have to do a lot more upfront research to convert this to a flow process. This optimization can be slow. When you're doing things with small tubing, you always have a clogging risk. The scope of the reactions that can be converted to flow chemistry is not every type of reaction, and you require highly specialized equipment and expertise, right? So there's a upfront cost that's needed. Okay, so biomimicry, again, just sort of as a FYI, in terms of the ways in which we can take, for example, biology that can create all of these different colors to apply this to solve different human problems. And so, if you think about essentially fossil fuels, essentially there's 3.8 billion years of experiments that were done to create those fossil fuels that we use today. And so essentially what we want to do is not say to ourselves that we want to replicate something that took 3.8 billion years, but we want to say that what was the design feature of that process, and then can we take advantage of it, right? That's the question that's most important, not if we want to replicate exactly what nature is doing. And so, you know, we can look at the microstructure of biological systems and say how it imparts strength in that in these microstructures, and then by understanding how that strength is why that is such a strong material naturally, we can then incorporate that into layered material architecture, right? So this is where we're taking the design feature, not replicating it exactly, but understanding it and then applying it to other targets. We talked about before the way that color is produced in nature is not always through dyes, but rather through the different layers or thickness of those materials. And so that's something which we could incorporate into textiles and dyes to reduce the amount of chemicals that gets produced. So again, just another example of the wing of a butterfly, and this, you know, Myrosol display technology, which is like, you know, on a screen, a display screen that sort of takes advantage of that same sort of design feature that comes from inspiration from nature. You know, low energy ventilation systems. So this termite mound has a very efficient way in which air can circulate through this system. And so again, that sort of design feature has been incorporated into architecture to be able to reduce the energy costs of these buildings. And again, taking design features from, you know, something which I would say is a very unusual inspiration. Repairing damage, this is another important one. So, you know, blood clotting, the way that our blood clots, that's a way that we repair damage that occurs on the human scale. And so this is again taking inspiration from things like that and many other examples of how nature repairs things. And so this is examples of repairing leaks. Like, so if we have a pipe that is leaking water, that's shown here. If we design the material in such a way that we can actually incorporate repairs to that doesn't involve, like, this is what I'm talking about, is repairs that are chemical, not physical repairs, right? So it's a difference between putting a piece of tape on top of the leak versus actually having the molecules modify themselves so that there's no leak that occurs anymore, right? So that's what is more similar to blood clotting as opposed to a physical repair, which would be just physically putting a piece of tape on top of it. And that's what's these self-healing material concept. And this is done, for example, on the wings of planes. They have self-healing materials. There's other areas where, you know, you can't have something fail in the middle of its use because the failure of a wing on an airplane would be catastrophic, right? So being able to design features that avoids that, to avoid those catastrophic disasters, is very important in certain applications. Hooks and loops. So, you know, this is Velcro, which I think that, you know, lots of people have used. Again, this is taken from a natural source. This is the burdock burr. So I don't know if you've ever experienced these, but, you know, essentially it's the same concept of Velcro, right? The tips of the two species intertwine with one another and creates a huge force that makes it very difficult for you to separate those two. And that's then just applied to polymeric materials with that same sort of interaction, just on a smaller scale, and you have the same ability to create something, a very strong bond between the two. And again, you know, it's difficult to replicate nature because nature has had so much time to design these features that, you know, for us to chemically replicate it is not practical, but so for a lot of these things, it's really the design feature and trying to do it as best as we can via chemical process. But we do know that, you know, energy capture is something nature does very well, and we need to find new ways to produce energy on this earth. And so nature is going to be one of the best ways in which we can do that. Flight and maneuvering. So, you know, airplanes can't maneuver in the same way that a hummingbird can. The way that it can go up and down, left and right very quickly is something which we can't do. And so it's something, again, that we might take inspiration. Navigation, so the way that these animals can navigate huge distances without any compasses, without any GPS, you know, is something that we can take inspiration from. Camouflage, the way that different animals hide themselves in their natural environments. Freezing tolerance, so, you know, the fact that some animals can exist at sub-freezing temperatures, so that means that they have some antifreeze proteins that prevents their bodies from freezing. That's something which is very interesting. And then high strength materials. So we all know that there's, you know, some animals that you try to, you know, insects or other bugs you try to peel off of a window and you can't get them off, right? So it's a huge amount of high strength material that's keeping them there. And so can we be inspired by that to create those types of materials? Green chemistry depends on element choice. So, you know, which atoms are we going to incorporate into our products that are useful? And this periodic table is just showing you essentially the atoms which are considered non-precious. So essentially that are highly abundant on Earth. So it's the gray atoms that are shown here. Then the yellow atoms are more less sustainable, and then the red ones are even less sustainable. So if you take a look at some of these, is that, you know, some of the catalysts that we use, a lot of the catalysts are based on things like rhodium and ruthenium, which are essentially more depleting than things like copper and iron, which are more sustainable sources of metals. So again, this is just thinking about, you know, if you're going to design new reactions with new transition metals, which one of these are you choosing? And is going to be very important. You know, helium has become very, very expensive over the last month because of what's going on in the Middle East. And so most of the helium that we use comes from the Middle East. So the price of this has doubled in the last month. And so for people that are using MRIs in hospitals, that's a huge problem. For people that are using NMRs in research, this is a huge problem. So again, like, you know, how are we going to solve this going forward? Because we have this technology, MRIs, which is life-saving, but we use something which is essentially like petroleum, which is a resource that is depleting and not replenishable. So we have to come up with creative ways. Are we going to design ways to make helium synthetically? Are we going to create MRIs that don't use helium? These are open questions that are important questions going forward. So essentially knowing that not all of the elements of the periodic table are equally scarce, I think is an important design feature for when you're doing your whatever projects and chemistries that you're doing. So essentially, this molecular understanding is the basis for substitution and redesign. And so again, this is why chemistry is such an important factor, right? Because essentially everything is made up of molecules. And so if everything's made up of molecules, then the atoms and the bond, understanding the atoms and the bonds and the molecules that go into the materials that make the products, right? If we understand that, that's how we can change things to make them more sustainable, more green. But without understanding that molecules come from bonds and atoms, understanding the stoichiometry, understanding the moles and grams, right? These very basic principles of chemistry is like, it's hard to see, long-term impactful positive change. So these are just some questions to ask based on what we talked about today. So essentially, when we look at a balanced equation, we have to look at what must be consumed to make the product. So what are the reactants and how many of those reactants are being incorporated into the final material? The molar mass, so how much material is handled, because ultimately at the end of the day, we weigh things in mass, grams of material. Reaction class, so different reaction classes have different amounts of byproducts. The solvents and the reactor type, so choosing solvents that are more on the green side versus the avoid side. The reactor, so this is using a microwave reactor, flow reactor versus a batch reactor. That can influence the greenness of your process. What hazard and energy are introduced in all of these, and then what are the feedstocks that you're using and the elements, so the elements of the periodic table, and what upstream burden does it create by using those. So essentially, something as simple as stoichiometry, which again, I said we learned in high school and we probably learned in Gen Chem, and then we sort of put it aside, but that is really not separate from sustainability. It's a core part of sustainability, because understanding stoichiometry is the way that sustainability becomes measurable. So how can we tangibly measure it? We have to do it via stoichiometry. Okay, so this is some key takeaways. The moles and the molar mass connect formulas to lab scale quantities. Balanced equations provide mole ratios. Reaction classes help predict products and waste. Nature offers strategies for us to be inspired by. And greener design is going to include all of these factors. And in some processes more of one, some processes more of another, but these are the key factors that we should look at. And if you take away sort of some key concepts from this course for your particular research, is think about in terms of counting atoms, tracking the units, balancing equations, evaluating your full systems. That will allow you to design for less hazard and less hazard and less waste. And so, this is just sort of a general question that you could ask yourself for a design a strategy. So if you just take a look at any reaction that you're doing, it could be a very simple reaction, could be one you're doing in the undergraduate lab, if you're TAing an undergraduate lab, and just think about it in terms of these questions and see how green or not green it is. And that's like, even if you're not doing it for your particular research, but you can do it even for the undergraduate lab. Right? If you're doing an undergraduate lab and you're showing them, demonstrating them a particular reaction. And this is one thing that every department that I've talked to about this has always appreciated, is that if you do this, you can do that same reaction that you do in an undergraduate lab, replacing the solvent for something which is more green and usually cheaper. And the department is going to be very happy, right? Because the department, the costs of running undergraduate organic labs or any undergraduate chemistry labs is relatively expensive, right? And what you want to do is apply these concepts of green chemistry to make it more green, and you can save the department some money, right? So it's an interesting way to apply this concept to something which is tangible in your actual department. Okay, that's it for this part today. We'll take a small break, but before we go, is there any questions? Did everyone get the first lecture slides? But not these ones yet. These ones too? There's two. Yeah, so I'll send the rest by email. Okay, let's take a break then. We'll come back.
A gente também não inscrito para estar no canal do INCT. E você teria, a gente não capricha, você pode ficar na lei, não ficar mais à vontade para falar, contigo, tá? Se você puder falar.
Excuse me.
Yes, yes.
When are you searching about materials and you have an expression with a biological system? How do you search? You go to a biological journal and read the news, or you have a problem and by the problem you go to search the solution about this problem with the system. My question is, how do you connect the news in the biological system, in journals of biological, with the chemistry questions?
Yeah, that's like a good question. It's not easy to do that. So it's like you have to read the biology journals, but the easier way is to try to collaborate with some biologists, right? Because the best way to do it is like you try to understand their perspective and then you bring the molecular perspective to them. And then you can like sort of really make something more powerful. But like if you're like, what you're saying is really great, but I'm saying there's not a lot of people who can understand all the biology and all the chemistry, you know? So that's why I'm like, I tend to think that I don't know enough biology. So I'd rather go find an expert and say, I'm interested in this. You're an expert. Let's see if we can figure out a way how to use what that is in a chemical way. But like then the problem becomes is that does the biologist actually want to collaborate with me or not? But if they don't, then I find another one, you know, that will.
Yeah.
So I think that like, but I mean, getting good ideas from biology journals, I mean, that's a great way to look at it, right? To at least figure out who you should talk to.
Nice.
Yeah.
I understand. Thank you.
Good question. Okay, so I just wanted to give just 2 or 3 slides on one of the research projects that a PhD student in my group was working on, and then a postdoc is now currently working on, and that's on this the synthesis of dienes. And so, we can look at different types of dienes. So these are what's called cumulated dienes. So essentially 2 alkenes that are not separated by a carbon-carbon single bond. So these are called allenes. They're very interesting molecules, but they have limited stability. They're challenging synthesis and limited industrial applications, although there are some interesting applications for these. There's isolated dienes, so essentially we have an alkene and another alkene, and if that alkene is separated by more than 1 carbon between the 2 of them, then they're 2 isolated alkenes. Right? So there's 2 of them, so it's a diene, but they're not conjugated with one another. And these are interesting, but they don't have conjugation, so there's practical limitations to how you can use them, limited reactivity because they're non-conjugated, and they're less effective as monomers in syntheses. What I'm interested in our group is these conjugated alkenes. So an alkene separated by a sigma bond, 1 sigma bond to another alkene. And so they are conjugated, they're stable, they're reactive in a variety of cycloaddition reaction. They can be used for polymerization reactions. So we think that they're interesting, and there's a lot of these dienes that appear in natural products and drugs. So here's a diene, 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 and a diene that's shown here. And so essentially, common synthetic strategies, common ways in which these are made are shown here. So we can have cross-coupling reactions with various metals. We can have essentially reactions to make alkenes from carbonyls or alkenes from XY groups. And we can, if we have an alkene already present, we can make the conjugated one. We can make an E9 reaction, or we can actually convert this allene from a non-conjugated system to a conjugated system by deconjugating. But every process, as we've discussed in green chemistry, is going to have some issues. So these tend to have harsh reaction conditions. They're conducted under inert atmospheres, so it's difficult to do these reactions under air. There's undesired byproducts limiting the atom economy, limiting the E factor, and there's low atom economy for these reactions. Here, same sort of issues. And so what we saw as an opportunity was this reaction, which is called the aldene reaction. So essentially it's taken alkene with at least 1 CH bond at the alpha position of this alkene and an alkyne, and it undergoes this aldene reaction, and this can form these non-conjugated systems. And if you see that in particular systems such as this one here, you can do it under palladium catalysis, and you can get a mixture of 2 different products. So this product is the 2 alkenes are not conjugated with one another, and this one it is, and you can bias this system to get one or the other. And so what we're interested in is biasing the system to get the conjugated alkene versus the non-conjugated alkene. And so a number of other research groups have done this with a number of different metal catalysts. So these are the sort of the proof of principles or the history of this type of reaction. And what we were building upon was this paper by Trost in 2009, which he did this reaction with ruthenium, but he did this in solution. And so this is the reaction that he was able to accomplish. So the different types of alkenes, different types of alkynes. It made what he proposed is some sort of Ruthenius cycle. That Ruthenius cycle could undergo demethylation in two different ways, but ultimately in both of them, you could get demethylation either to get to the non-conjugated diene or the conjugated diene. And he was able to show mechanistically that there was a few ruthenium species that could lead to one or the other. So the solvent of this reaction was acetone, and you can see that acetone market size, the prediction out to 2034 is huge. So there's a huge amount of acetone being produced, but that means that there's a huge amount of acetone that needs to be disposed of, right? So that's one of the issues, that even though the acetone is abundant, it's something that we want to always try to avoid. And so this is where we essentially are interested in moving away from using solvent. And so, annually 20 metric tons of solvent is produced on an industrial scale, and much of that solvent needs to be disposed of. So essentially 80 to 90% of the total mass of any reaction is the solvent. And so this is the largest component of the waste in any chemical reaction. Organic solvents react in the atmosphere and sunlight to form air pollution and ground level ozone, which is negatively impacting our environment. And so this is where I told you about our interests in mechanochemistry. And so again, I'm just giving this as a brief introduction just to think about why we use mechanochemistry. And I think that, these are the tools I showed previously. So the ball miller, the orbital mixer, just a simple mortar pestle. So really we can have benign reaction conditions, short reaction times, and we can minimize the use of solvents. And we can get increased selectivity. And the reason why we can get increased selectivity is if we have to look at the rate of these chemical reactions that's essentially governed by this Ernst equation that we learn in kinetics in any undergraduate class. But what's interesting about this equation when we think about how we control chemical reactivity and the rates of different chemical reactions is that oftentimes what we're doing is we're controlling reactions by temperature, right? So temperature is what we're using as a modifying factor, but what we are not changing when we're doing things in solutions, we're not using the Arrhenius constant, which is the A factor, to change the rates of the chemical reaction. So remember, K is the rate of any chemical reaction. So by changing temperature, we have a greater effect on the rate because it's in the exponential. So the EA and the T components have a greater effect because they're in the exponential. And that's why we tend to focus on those to control chemical reactivity. But the A factor, it's not part of the exponential, but it's the amount of collisions that happen in a chemical reaction. And so even though it's a less important part of the rate, it is a part of the rate. And that's where we think that mechanochemistry is going to have a much greater impact, because the temperature is not going to change a lot in the ball miller because we're not adding an external heat source. But what we are increasing is the amount of collisions that happen. And so we're changing the A factor, which is very different, which means that if you have two processes, one leading to a productive production of your desired product, and another separate chemical reaction that produces unwanted byproducts, if the rate of collisions is a factor in producing one over the other, you can increase the selectivity mechanochemically. And so that's why mechanochemistry can be an underrated way in which you can increase the selectivity of certain reactions. And so you can increase the stereoselectivity, the regioselectivity, the chemoselectivity. And so if you see here, essentially what we've done is we've taken their conditions, which was room temperature 1 to 4 hours in acetone, and we have been able to do that reaction in about 30 minutes at 30 hertz with barium titanate to add as an additive to the reaction, and we get similar types of products that they got previously in this reaction. So the one thing that you should, based on what we've talked about in this course, is to think about, okay, you removed the solvent, that's good, right? But you added barium titanate, right? So if you really want to think about this as a green process, you have to think about what's more economical in terms of greenness, is removing the acetone or using the barium titanate, right? And the barium titanate, we're using a 1.5 equivalent, so 150 weight percent. So it's way less than the acetone, but we're still using something which is not used in the solution chemistry. And again, what I'm imparting on you, even though we think this is an improvement, but you should critically judge this to say that we have to look at everything. And the barium titanate is something that wasn't there. So is that actually improving things, or is it not? So again, I'm not going to go over the details of all of the rest of the project, the optimizations, the kinetic studies, but I think that is just giving you this. I think the take-home message is that a factor in the rate equation can be controlled more effectively mechanochemically than it is in solution. Okay, so this is a continuation of what we talked about. I think we'll maybe go for about 30 minutes and stop. So essentially what we talked about before was the number of atoms that we have and how stoichiometry is important in determining atom economy. But what about other factors in the reaction, which includes the limiting reagent, the yield, and then how these affect the atom economy of the reaction, and how we can show this in a few examples of what we mean by these. So again, what we talked about before is that we convert moles to determine yields of chemical reactions. Then we can, based on the yield of the reaction, we can then factor in things like atom economy and E factor. And then once we take into consideration all of these, we can then essentially make a better decision on whether the process is improved or not in terms of its greenness, and its green, how green the process is. So again, this is simplifying what we talked about before. So if we have two starting materials that have to be combined to form a product, then that product is generating some sort of leftover excess reagent. We have to take into consideration the stoichiometry of these reactions, but we also have to take into consideration if there's any excess reagents that's required for this chemical reaction. So one of the things that we don't talk about in this, I didn't focus on, but it's this arrow here, right? This arrow here, we know that for chemical reactions, it can either be a forward arrow, which means that that reaction is, in theory, irreversible, right? Every chemical reaction, in theory, is reversible. But when we put the forward arrow, what we're saying is that that's for practical purposes, it's considered irreversible. But many, many reactions are equilibrium reactions, right? And so equilibrium reactions mean that they're going forwards and backwards. And in equilibrium reactions, how can you increase the forward direction of the production of the right side of an equilibrium? Does anybody remember? So if we have an equilibrium reaction, A plus B goes to C plus D, and we want more of C plus D. How? Exactly. So in undergraduate courses, what we say is that A plus B and C plus D is equilibrium. Well, just put more B, right? If you put more B, you push the equilibrium to the right, right? That's Le Chatelier's principle. And that's the way that you get more C and D. Now, if we think about it that's a great undergraduate teaching. If we think about it from a green chemistry perspective, how green is that? You put in more B, but you're not producing more C and D, right? The more B you're putting is to push the equilibrium, because one of A reacts with one of B to make C and D. So if you put two Bs, what's the other B doing at the end of the reaction? It's there still. If you put 3 Bs, 4 Bs, if you have to put 100 Bs to get the equilibrium to shift, you got 99 Bs left over that's you got to deal with, right? So from Le Chatelier's, that's why we don't think about that as an undergraduate concept, because we're just saying, okay, we just want to shift the equilibrium. We're not talking about what do we do with the leftover material, right? So what's the other way that we can drive that equilibrium forward? Is we can remove C or D, right? So now if you remove D, right, then you get more of C. So that would be a better way to shift it, right? Because if you're removing D, right, you're removing one molecule of D as it's forming, so you're not creating more waste, right? Because it's one molecule of D and you keep removing it, you keep shifting the equilibrium in this direction, right? So that's thinking about it, and both of them are equally chemically good answers, but from a green chemistry perspective, one is way worse than the other, right? And that's where a lot of reactions are equilibrium reactions. And so you have to think about that, how you can force those reactions going in one direction or the other. And so this also means that, if you have to put in an excess amount of one of those reagents, is that you're creating additional waste? And how do you deal with that waste? Can you recover the material? Can you recycle it? Can you put it back into another process? So we have to balance the equation, convert the masses to moles, use the stoichiometric ratios, find which reagent runs out first. So what's the limiting reagent of a chemical reaction? And then we use that limiting reagent to calculate the product amount. But essentially, the limiting reagent means that there has to be something in excess. And so what do we do with that particular waste? And so, a fertilizing plant, which is producing ammonia and CO2, it must be matched by mole ratio to make the urea of the product of this, which is the fertilizer, efficiently. So how much ammonia to CO2 do you use, and do you have to use in excess of one or the other to make more of the fertilizer? That's an important question industrially. So here's, just some examples to sort of give us an idea. If we have a 1-to-1 ratio of these two reactants, and we have 1 gram of each of these, and then we convert that to moles, we know that the smaller amount is the limiting reagent. So 0.0167 is smaller than 0.25. So that means that this acid here is the limiting reagent, and it means the sodium hydroxide in this case is the excess reagent. So we have to remember that when we're determining what's the excess reagent, we don't determine it by mass, we determine it by moles, but the amount of sodium hydroxide that is in excess is the difference between these two multiplied by the molecular weight of sodium hydroxide. So that would give you the amount, the grams of excess sodium hydroxide, right? So it's just important to remember this feature all the time, right? Is that what is the excess reagent? We determine that by moles, but the waste that we produce is measured in a mass, right? And so that we have to convert back and forth between the two to understand what the problems or the opportunities are to increase the greenness of a process. So, another example here, again, we should be relatively comfortable doing this, but if we have 6 moles of water and 2 moles of lithium that are mixed together, well, we know that that since there's a 1-to-1 molar ratio of lithium to water, that if we're using 6 millimoles of water, that we have an excess amount of water in these reactions. And so we can calculate this then based on the moles of lithium hydroxide and hydrogen that are going to be used, and that has to be calculated from the limiting reagent, which is the 2 moles of lithium in this case, and not the 6 moles of water. And that would give us that we would form 80.57 grams of lithium if water is used in excess as it is in this case. So again, just to make sure that we convert things to moles, but we understand that mass is what we have to dispose of at the end of any chemical reaction. So again, this is just the calculations. I'll leave it to you to refresh that if you do need to do so. Okay, so then this takes us to essentially theoretical yields versus the actual yield of the reaction. So again, the theoretical yield is going to be based on the limiting reagent. So we have to know the stoichiometry of the reaction, and we have to calculate the moles of each of them, understand the stoichiometric ratio of the reactants. Then we use whatever is the limiting reagent to calculate the moles of product, which then can be converted to the mass of product. And that mass of product is what we use as the theoretical yield. The actual yield is usually lower because reactions are incomplete, side reactions occur, and material can be lost during purification. So that's why we actually we calculate the theoretical yield 1 gram, and then we measure the final product mass that we get, 800 milligrams. We say the yield is 80%, but then there's 20% that's been lost. And so then it becomes a question of what happened to the 20%, right? Did it get lost in incomplete reaction? So that's where you look for, do I have unreacted starting material? Did it get lost because there's a side reaction? What is that side reaction? How can I minimize that side reaction? Did it get lost because the purification step decomposes some of the material? And I have to try to figure out different decomposition methods. So this is what I tell my students, is that when you're doing a chemical reaction, I feel like, and this is, I don't want to diminish what I'm going to say, but I hope you'll understand, is that I feel like it's a war of me versus nature, right? And it's a war to get that yield as high as possible because nature is trying to take my yield down, right? It's trying to take my yield down by byproducts, by purification, by decomposition, and it's my battle to try to battle all of those things to try to get the yield as high as possible so I don't lose it from all these little things. Because if you lose 1 milligram here, 1 milligram there, 1 milligram there, you can decrease your yield very quickly when you're doing things on a small scale. So that's where it's really, but even more importantly than just getting the yield up is to understand why is the yield low, right? What step is causing that? And if you can understand that, that's the step then that you can solve the problem. And then every time you get the yield up, you can generally then improve E factor because you're generating less waste. And the atom economy is based on the chemical reaction that you've chosen, right? So you can't solve that by increasing yield. So this is just, again, another calculation of this reaction. So we're starting from a limiting reagent of the acids that we're showing here. So we use that amount of acids to calculate the amount of the acetate that we form. So there's the moles times the molecular weight of the acetate. And this gives us the grams of the acetate that can be formed. We take the same limiting reagent times the molecular weight of water, and this gives us the grams of water that's being formed. Again, why is this important? Well, if our product that we want to actually isolate is the acetate, we see that this process is generating 1.37 grams of the desired product to 0.3 grams of undesired water, right? And so water being innocuous, relatively benign waste stream, so not hugely problematic to get rid of, but it's just important to note that that ratio is actually positive for our product. If that ratio was inverted and we actually wanted the water, then we are creating a large amount of acetate to a small amount of water. right? Even though the moles of each is the same, right? So the moles of each that we create is the same, but the mass of waste that we create is significantly different depending on which of these two that we're looking at. And then the actual yield, this is what we weigh at the end of the chemical reaction. We have 500 milligrams. We divide it by the theoretical yield times 100, and that gives us the percent yield. And so this is a useful, right, because we do industrially, they do want the yields to be as high as possible, but it doesn't take into consideration all of the things that we've talked about to really measure the overall process, right? And that's why yield is not a factor just in and of itself. So here's the example with urea and CO2, ammonia plus CO2 to make urea. So again, if you take a look at that, if we're going to do a reaction with 637 grams of ammonia with 1.142 kilograms of CO2, we need to do all of these calculations and see what the percent yield would be if we actually have 500 grams of urea at the end of this reaction. I think this is on the next slide. So we convert both the ammonia and the CO2 to the moles by dividing by the molecular weight. We see what's the limiting reagent. So here the CO2 is the limiting reagent. So we use the CO2. We have to convert this based on the 2-to-1 ratio of 2 moles of ammonia to 1 mole of urea. And so we have to divide the moles of ammonia in 2, so it's 18.7. So here, even though we have 37.41, because there's a 2-to-1 ratio here, we have to actually divide the amount of ammonia by 2. So now we're comparing 18.7 to 25.95. So the limiting reagent here is ammonia, not CO2. So this is where stoichiometry is very important to remember, that we have to convert when they're not equivalent. So it's not 1-to-1 stoichiometry. We have to correct for that. We then calculate the yield of the final product. So 18.7 moles of urea is formed because we have 18.7 moles of ammonia. That's the limiting reagent. Multiplied by the molecular weight, that gives us 1.123 kilograms of urea. And since our yield, we said on the previous slide that we got 500 grams, so that gives us a yield of 44.5%. But importantly, the amount of leftover CO2 is 25.95 minus 18.75. That's how many moles are left over. And so that's the moles of CO2 that is unreacted because it's excess. And that means that we have 319 grams that's unreacted. Right? So this is taking into consideration the full analysis of a chemical process, right? We have to say which of these is the limiting reagent, what's in excess, how much of it do we have left over, and we should go one step further, which we didn't do here, but we should calculate the amount of water that gets formed too, because that's another component of this reaction. We don't do it for water typically because, like I said, water is relatively green, and so we can usually separate that out relatively efficiently, especially in a process that's so well known like this one here. But it's just to say that it's one thing to say that we've got 500 grams of this at the end of the reaction, but what we really have is 500 grams of this, 319 grams of this, CO2, and then whatever amount of H2O. That's what we physically have at the end of the reaction, and that's what we have to deal with, and that's what we have to evaluate overall in terms of what is green and what is not green. So the percent yield answers how much of the desired product that we have. And if we think about it, that's sort of such a small answer to a very complicated question, because we don't answer how clean or safe was that route, right? And so we're ignoring a lot of factors. So like the co-products or the byproducts, how much solvent is used, can it be recovered, can it be discarded safely? Any reagents, are there excess reagents? Is the waste hazardous? So like water, not hazardous. Sometimes the wastes are more hazardous. How much energy was needed for heating, cooling, or purification? Is a catalyst used catalytically or in stoichiometric quantity? So sometimes we have additives that can be used, in 1 mole percent, very good. Sometimes they have to be used in 100 mole percent, not as good because they can't. Then that's a waste stream that you need to purify. And so that's where, these terms that I've introduced, atom economy and E factor, can be used to evaluate these types of processes. So this is just essentially more specific examples of terms that we've generically talked about to this point, but talking about atom economy. And so atom economy, in terms of the number that you can use to calculate, is the formula weight of your desired product divided by the formula weight of all the products that are formed. Right? So basically, you take the formula weight of your product, you add in the formula weight of all the byproducts, and you multiply that by 100, and that can give you an estimate of how many atoms that you started with were incorporated into your product versus how many atoms that you started with that were incorporated into the byproduct. It's a ratio, so it just gives you an idea. The higher that it is, the more that have been incorporated into your desired product, and that's what you want to aim for. So the yield asks how much desired product did I isolate? Atom economy says how much of the starting material became the desired product. So 100% yield with a large co-product can still be a reaction design. So you can have something 100% yield, but if it has a low atom economy, then that is creating a large amount of waste, right? So 100% yield, low atom economy is an inefficient process. So that's why examples where yield only tells part of the story. So that's why the barium chlorides to barium sulfates example that we showed previously, it's a good example of this. Because if you look at this reaction, the desired product is barium sulfate, which has a molecular weight of 233.4. The co-product is HCl, 72.9. So if you do the ratio, so remember the ratio is the molecular weight of the desired product divided by the molecular weight of all of the products, the potential products. And so here we also have to take into consideration stoichiometry, right? So 1 barium sulfate makes 2 HCl's. So that's why the co-product is double the mass of HCl. It's not just HCl on its own. And so it's 2 HCl's, which are 72.9. And so the atom economy is 76.2. It's relatively high, but it's not perfect, right? So this is an example of, if you had 100% yield and 76.2% atom economy, probably pretty good. If you have 50% yield and 76.2% atom economy, not so good, right? So this is where we have to take into consideration multiple factors. For this, if we look at another reaction, so sodium carbonate plus calcium hydroxide to form sodium hydroxide and calcium carbonate, if the desired product is the sodium hydroxide and the co-product is calcium carbonate, again, we can do the calculation of the atom economy. So the atom economy now is only 44.4%, right? So most of the mass is in calcium carbonate. It's a bigger molecular weight. And so therefore, the atom economy of this process to make sodium hydroxide, now again, this might not be the most efficient way to make sodium hydroxide. It's just a sort of an example to give you an idea that these are the types of calculations that you should do to measure the efficiency of any chemical process. So this is just an example of the synthesis of ibuprofen. And so starting from this benzene, isobutyl benzene that's shown here, you can do one step, which is the acylation of this reaction. So this, again, is a Friedel-Crafts reaction, which I said previously is not atom economical, but it has been used industrially for a number of different processes, including ibuprofen. This acylated product, then you have to do 2 to 5 stoichiometric steps. So between 2 and 5 steps between this and this. And if you think about what's happening here, all that we've done is we've added in this cyano group here, and we've chopped off 2 carbon atoms. So in terms of the efficiency of the process, we have done a lot of steps to not do too much to the molecule, right? So this is just another subjective way to think about the efficiency of the synthesis, right? Is that you want your molecule in every step to get more and more complicated, because that's usually the most atom efficient way to get to the final product. If you have to chop parts of the molecule off, right, that's pretty wasteful, because you're going from high molecular weight to low molecular weight products, right? So that's sort of, you're going backwards. It's not to say that you can't do it, but in terms of atom economy, you're not going in the right direction if you've built this with more carbon atoms or less carbon atoms, depending on the left or the right side of the molecule. And so the BHC catalytic route is essentially doing the same first step, except that they've optimized it to do it without a lot of excess reagents. So the E factor for this is hugely improved. They've done a next step, which is a catalytic hydrogenation. So it's only adding H2. It's a single step. And then in one step, they're doing a carbonylation reaction where they're adding in the carboxylic acid that's shown here. But that carbonylation is coming from CO, which is introducing those 2 carbon atoms. And it doesn't show it here, but it's water that's introducing the OH that's shown here. So from an atom efficiency standpoint, you've got very few excess atoms here. So this improved synthetic route of ibuprofen is much improved. 3 steps that are catalytic. So, and this is small quantities of the catalyst. So very little materials required. 80% of the atoms are utilized in all of the steps, and up to 99% when acetic acid is recovered. So out of all of the atoms that are used in these reagents, if you recover the acetic acid, that's the most wasteful atom in the chemical process. It's from the acetic anhydride. So if you take that acetic acid and you convert it back to the acetic anhydride, you get 99% atom efficiency. There's fewer steps, there's less reagent mass, there's fewer separations, and so the overall process is way more efficient than it was. And this basically is a classic green chemistry example, because it delivers the same drug with a much better process design. So this is an example of the original process, and that original process was an industrial process. It was redesigned after the fact based on the green chemistry principles, both to reduce the costs, but also to improve the environmental impact, reduce the environmental impact of that synthesis. Okay, so this is E factor. So again, we talked about this before, and you know what? I think that we'll end there for today, and we'll start again after the student presentations with E factor next class. If there's any questions, I'll be happy to take it before we stop.
E você vê que às vezes algo tem um rendimento maior, a não ser algo tão verde assim. Isso.
So, what is that means? We have a prompt, has a practical use of 40%. So, looking at new characters and align with other activities. We can find another prompt that has a higher use, but it's not so.
Yeah, so that's a good question. Like, so the thing about yield, like where I say that it's not the most important factor, it's not, but it is a critical factor. So I would say that, like, you know, no industrial process that I know of is going to have a yield of 40%. So you have to have the yield high, and, you know, high can be subjective, but I would say like sort of 80% is in the range and above. But then it's just that you have to have all of the other things high as well. So you have to have the E factor, and the atom economy and the E factor have to be. So basically it's to say that, like, you can't sort of sacrifice any of them. But it's like, but you can't also say that I'm going to put one of those so low and hope that atom economy and E factor will just cancel everything out. Because at the end of the day, if you have 40% yield, it's hard to get your E factor high, because 40% yield by definition means you have 60% that's waste, right? So you're already like sort of like behind, like, you know, you can't overcome that, because it's like, what happens to the other 60%? It's not useful because it's not part of your yield. So that by definition means it's waste. So that's why it's like essentially E factor and yield are kind of related to each other. And so you got to get that yield high enough so the waste is low enough, which means the E factor is improving. And so I think that that's, you know, an important thing. But, you know, I think that if you get something, you know, if you have a process like, you know, if you have a process like this, right, where you are just adding hydrogen and you have like a tiny amount of catalyst, and those two hydrogen atoms are incorporated into your final molecule, then you can have your yield come down a little bit, because the amount of waste is so little, right? Because there's nothing, the hydrogen is completely incorporated and the catalyst is tiny quantity. So then it's like where yields can come down, because your waste is so little outside of the reagent, the starting material. So if you have any excess leftover of this, that's your only waste source. So that's why if you have 70% yield, then you can deal with that sort of waste. And again, it's highly dependent on, you know, the industry you're in. So like this, most of the time when I'm talking about from the pharmaceutical perspective, because if you're talking about from the petroleum industry perspective, they might say that, you know, the difference between 99.99% yield and 99% yield is unacceptable to them, because they are like, you know, they're really trying to get everything optimized perfectly, because they want zero waste, so that it produces all of the byproduct, and that all of that byproduct gets converted into something else, and all of that byproduct gets converted. So for petroleum, it's like sort of the standards could be way different than the pharmaceutical industry, because like that chart that I showed you, the E factor of petroleum is almost zero, and for the pharmaceutical, it was between 25 and 100. So for them, they're willing to accept more waste because their profit margins are huge, and whereas petroleum's profit margins are small, so they can't afford any waste. So, you know, it has to do with economics as much as it does science sometimes too.
One of the might be what three is most important yet. Because the guys from Forgione, as you said, they study a lot of this kind of reaction, and I think the way to reduce the steps, the number of steps.
Yeah, no, I think that's like, we talked about it yesterday, you know, and it's like multi-component reactions. Certainly that's like a great way to do it, right? You know, and again, it's like nothing's perfect, right? But I'm just like multi-component reactions in a way resembles nature, because that's the way that nature assembles things enzymatically, right? Nature's really great at designing an enzyme that can bring together multiple molecules and put it into a particular site and then react those to reduce the entropy of the process. And multi-component reactions are sort of mimicking that. It's just, as with everything, is that when we try to do something chemically that nature does so well, it's like, how do we get that to be efficient? Because you need one process to happen before the next process, in a multi-component process. And how do you get that order to be correct so that you don't have off-target reactions? Because sometimes if you get one and it gets stuck and it reacts with something else, well, then that leads to a byproduct. And so then it's like that byproduct now is waste, but now is that an irreversible reaction or it's a reversible reaction? If it's reversible, well, then how do you get that to come back to here to go to the final product? Is it a thermodynamic driving force that gets you to the final product? If it is, then is it in general for all of the substrates, or is it specific for the one substrate that you're doing? It becomes really complicated, but the amount of solvent that you can save by doing 3 reactions in one pot, I mean, that's a huge savings, right? So then it's like, yeah, maybe 50% yield in one pot versus 3 70% reactions, right? That's, yeah, absolutely. So it's like, yeah, it's like, so multi-component reactions definitely, like, can be considered green. It's just that, again, not to, repeat this stuff all the time, but it's like, you can't just say multi-component reactions are green, right? You need to evaluate the whole system, right? So you're saving, what's the atom economy, what's the E factor, and then compare it to the non-multi-component reaction, and then it's a relative thing, right? So this is more green than this process. That's fair to say, but to say something is green or not green, it's not possible, because that's an absolute thing, and it's not absolute, it's relative.
Another possibility, not always.
Yeah, exactly. And again, like I said yesterday too, is that we sell our science as green, but it's not green, right? It's just another tool towards green, right? Because we do things, like I think it's just important to try to be honest about what you're doing, right? Because I showed you the mechanochemistry stuff, and I said we removed the solvent, but I have to be honest and say, but we have barium titanate, right? Which they didn't have when they did it in solution. So which one's greener? It's a deeper question, but when I go sell my paper, I try to sell it the most positive way possible, right? That's the way that science works, right?
It's way too complicated. It's too complicated. System is very, isolated, because every system is a system, so we have to do it.
Yeah.
One thing I found interesting is that, like you showed, what you can reducing the steps makes the reaction green, and it's very important. But sometimes the number of steps is also problematic for multi-component reactions. There are a lot of steps, but they afford just by themselves the thermodynamics. The reaction, the sequence of reactions flows naturally. So we have, despite we have a lot of steps, it just afford naturally.
Yeah. So I think that, like, to be more precise, it's when I say a step, it's not the number of chemical reactions, it's the number of reaction vessels you have to load. Exactly. It's what you physically have to do all of these steps. If the steps are all in one reaction vessel, then that's one step, no matter if you know, and I think that a good example of this is polymer chemistry, right? Polymers, you take one monomer and then it repeats itself. So the number of steps in a polymer reaction is, you know, thousands of reactions, but it's one synthetic step because it's one reaction vessel that you use. But the number of reactions that occur in that vessel are on the order of thousands of reactions, right?
Question about can be for small bones or with methodologies
No, I think that like multi-component reactions, it's like there's no limit as to the size of the molecule. It's like the limiting factor is the creativity of the scientists that can, you know, figure out reactions that can occur in the same reaction pot and are compatible with one another. You know what I'm saying? So that it's like reaction A and B and C all can be done without the functional group of C reacting with the functional group of A. Right? So it's sort of the functional group compatibility that you're doing something here and whatever happens here doesn't rely on the other things, but it does benefit from the new functional group that gets converted. So it's just sort of, you know, this deep understanding of molecules and saying to yourself that, like, you know, this reaction creates this functional group, and that functional group is the starting functional group for the next reaction, right? And then that creates a new functional group, and that is the starting point for the next reaction. But all of those functional groups don't interfere with anything that happens previously, because at any one time, you could have any of those materials present, because, you know, again, this is where it comes down to moles, is that we don't have a single molecule. Because if we had a single molecule that went to this, then we wouldn't have to worry about incompatibility. But we have moles of molecules. And so if one molecule goes to here, we have one molecule and thousands of unreacted molecules. So how do they coexist until those all become this? And then that goes to the next one, and there's one molecule in all of these and all of some of these. And so they all have to coexist. And that's where it's like the multi-component reactions are really like powerful, because they can do that, but it's really challenging to make sure that they don't cross-react with one another, but they only react in the order that you want them to occur. And again, I'm certainly not an expert. I'm sure that you can say much more about it than I can. Nice. Great. Thank you, everybody, again.